Section 5.2 is direct variation. I can write and graph an equation of a direct variation. Big ideas here. If the ratio of two variables is constant, then the two variables have a special relationship called a direct variation. The graph of a direct variation equation, y equals k times x, is a line that passes through 0, 0 and has a slope of k. Direct variation is a relationship that can be represented by a function in the form y equals k times x, as long as k isn't 0. So the constant of variation for a direct variation, our k value, that's our coefficient of our x term. The ratio of our variables in the direct variation equation is constant. It's our y over x, just like it is for slope. Remember, our k value represents the slope in our equation, and we find slope by taking y's over x's. So here, it's y over x because it's for a specific point. So we can also get that from our equation up here. If I solve for k, I divide by x, and I get y over x equals k. To determine if an equation represents a direct variation, we solve it for y. So y equals k times x. If there's anything added on at the end, it's not direct variation. If it's not just an x, if it's x squared, things like that, then it's not direct variation. So, does the equation represent a direct variation here? If so, find the constant of variation. So the first thing we're going to do is we're going to solve it for y. Y equals, I'm going to write it as 2 over 7 times x. 2x over 7 is the same as 2/7 times x. So is this direct variation? Well, we compare it to y equals k times x. Here we see it's in the same format. We have y's equal something times x. So yes, it does represent direct variation. So now we need to find our k value. K equals 2 over 7. It's our coefficient. It's our number that's being multiplied times our variable. In B, again, I'm going to solve for y. So on the same side as my y, I have another term being added. So we're going to go ahead and subtract that term. And it doesn't matter that it's a 4x. We treat it just like it was anything that's being added on. Again, we always get rid of any adding or subtracting first. Here, I'm going to write this as negative 4x plus 8. I'm going to put my variable term first. And I can't put the 8 and the negative 4x together because they're not like terms. They don't have the exact same variable. Now, I can solve for y by getting rid of my multiplication by dividing. And remember, when we divide both sides, and we can distribute that division, just like we did in chapter 1, I think, maybe 2. And we get y equals negative 4 over 3x plus 8 over 3. We divide that entire side, and remember, division bars is a grouping symbol for division. So we can take the 3 to the negative 4 and to the 8, and since it started as division, it stays as division. Now, when I compare this to my direct variation equation, y equals k times x, I have this extra 8/3 here that doesn't fit in my equation. So this is not direct variation. So we don't have a k value. Now, does 4x plus 5y equals 0 represent a direct variation? Let's solve for y and check. First thing I'm going to do is subtract a 4x. Whatever I do to one side, I do to both. Anything that doesn't have a y has to go to the other side. So what I have here is 5y equals 0 minus 4x is just negative 4x. And I know in the last one we couldn't put the 8 and the negative 4 together, but 0 is its own thing. 0 plus or minus anything is that thing. So now we get rid of our 5 that's being multiplied by dividing. So what I have here is y equals negative 4/5 x. We want to know, does this represent a direct variation? So we compare it to our direct variation equation. All of our pieces match up. We have a y equals some coefficient, our slope there, our k value, and our x's. There's nothing extra, which means, yes, this is direct variation. And then it asks, what is our k value? K equals negative 4/5. In example 2, we're going to write a direct variation equation. It says, suppose y varies directly with x, and y equals 35 when x is 5. What direct variation equation relates x and y? And then what is the value of y when x is 9? So we're looking for two things here. We're looking for a direct variation equation, and we're looking for the value of y. Here it says y varies directly with x. Y varies directly with means equals k times x. So y varies directly with x. Then it tells us y is 35 when x is 5. So we plug those in for y and x. We can solve then for k by dividing by 5. And I get 7 equals k. So the first thing they wanted here was what direct variation equation relates x and y. So we need an equation that has both an x and a y in it. So I'm going to go back into my original here, my form, and plug the k in. Y equals 7 times x. Again, we need an equation that has an x and a y in it, and the relationship, and that relationship is 7x. My constant of variation, k, is 7. So this is the first part of my solution. Then it says, what is the value of y? So we're looking for y. When x is 9, we substitute that in and simplify, and we get 63. So according to this relationship, if y is 35 when x is 5, then when x is 9, y will be 63. We have our equation, we have our solution for y. Now, suppose y varies directly with x, and y equals 10 when x is negative 2. What direct variation equation relates x and y? What is the value of y when x equals negative 15? So we're looking for two things here. It says, what direct variation equation relates x and y? So I'm looking for an equation. And then it says, what is the value of y when x is negative 15? So suppose y varies directly with equals k times x. Then it tells us y is 10 when x is negative 2. So I plug those in for my x and my y values. I still have my k. And what that lets me do then is I can solve for k by dividing by negative 2. Being multiplied, we get rid of it by dividing. And I get negative 5 equals k. Now that I know what that is, I can find my direct variation equation that relates x and y. Again, in order to relate x and y, they both have to be in my equation. So I need a y, I need an equals because it's an equation, and I need an x. So here is my equation that relates the two. Now it says, what is the value of y, is what I'm looking for, when x is negative 5? Well, I plug in, negative 15. I plug in the negative 15, and I get a positive 75. And both questions here are answered. Example 3 is graphing a direct variation. Weight on Mars, y, varies directly with the weight on Earth, x. The weights of the science instruments on board the Phoenix Mars lander on Earth and on Mars are shown on page 302, and I have a picture of it here. What is an equation that relates weight in pounds on Earth, x, and weight on Mars, y? So here we're looking for an equation. which means it's going to have an equals. It says y varies directly with x. And it explains what those things are. Weight on Mars, y, varies directly with weight on Earth, x. So the weight on Mars and weight on Earth, those are just the labels for our variables, which they give us here. So y equals k times x. Then if we look at our picture, it gives us some information. It tells us that on Earth, it's 130 pounds. So Earth is x. I put 130 in for x. And on Mars, it's 50. And Mars is y. So I put 50 in for y. And now I can find my k value. K is being multiplied. I get rid of it by dividing. Whatever I do to one side, I do to both. Here, 50 over 130, we always want to reduce our fractions, but since we're talking about our k value, which is slope, I'm going to leave it as a fraction for now. Now, my equation is what I'm looking for, so I take my k value and plug it back in. So y equals 5 over 13 times x. And that's my equation that relates weight in pounds on Earth and weight on Mars, y. In part B, it asks, what is the graph of the equation in part A? Here, we can use our function y equals 5 over 13x and the information it gives us. So it tells us that weight on Earth is x and weight on Mars is y. So I'm going to make those my labels on my graph. Since weight on Earth is x, it goes on the bottom. Since weight on Mars is y, it goes on the side. Remember our axes, x is always the bottom, y is always up and down. So left and right, x, up and down, y. Now with direct variation, we can set up a table, and with our table, we plug in values for x and get out y values, the same way we did with other function rules. So because we're talking about weights here, I'm going to start at 0. And we could just go 0, 1, 2, but a lot of the things that we're going to take to Mars are probably going to weigh a little bit more than that. So to figure out their weight on Mars, I'm going to go by 10s or 50s or however you want to go. So I'm going to go by 50s. Because some of that equipment and the people and things like that are a lot heavier than 2 pounds on Earth or 10 pounds on Earth when you think about those like big rovers and things like that. So this will give us kind of an idea there. Now that I have my x values, my inputs, I plug them into my function. I replace my x values. And here, because it's an application problem, I'm actually going to evaluate those and get decimal approximations, because if I say 250 over 13, that's not super helpful. So there are my approximate values. Now for scales on the bottom on my x-axis, I'm going to go by 50s, since that's what I counted by here. On my y's, I'm going to go by 10, because I need to get all the way up to 77. And on my x, I actually made every 2 lines 50, so I went by 25s there just to kind of spread it out. Then I plot my points, 0, 0, 50, 19, 138, 150, 58, and 277. I can connect those and put an arrow because it continues up.